Hi everyone and welcome at Vision Components. If you're planning to integrate an embedded vision solution into your next application, it's the right spot. Stay tuned. I'm Jan-Erik Schmidt from Vision Components, and today I'm going to show you 3 different ways of how to integrate an embedded vision component into your application to create a perfect solution. We will start with the most flexible way, is using very compact MIPI camera modules that can be interfaced to a lot of different CPU units, and you have a, let's say, broad choice of different image sensors. Next level would be a much more integrated but still OEM board level type of solution where you can get the image sensor, different image sensors together with the CPU unit, the interfaces, the memory and board, everything you need to create an application on one single small board. The next level, which we will call, let's say, the final level of embedded vision solutions, is the integration of what we've seen earlier, but in a ruggedized housing with industrial connectors and optionally a lens and a lighting if it fits to your application. But now, before we get started to go into details, we go a bit back in history, about 25 years, to show you how everything in embedded vision started. So it's the year 1996. So let's say it was a year of a lot of technological advance. First, Dolly the sheep, the clone sheep, has been born. Then we had Deep Blue, that was the first machine intelligence to win against a human being, a human chess master. And we had Michael Engel inventing the first smart camera worldwide. It was the first smart camera that was meant for serial production and for industrial use. And this development was more or less the result of, at that time already, about 15 years of experience from Michael Engel in the machine vision industry. And all this experience, what is really needed to successfully implement a vision solution, was, let's say, then concentrated in a very compact design. So it was his vision and his idea to get rid of external components, to have the camera on one place, then a lot of cabling to go to a PC, and to shrink everything together in one compact design. To put everything that you need, meaning the CPU performance, the image acquisition, you need, of course, the storage, direct SPS, PLC connection on board, a video output, to put everything in a very compact design. And of course, the experience to have a successful implementation in the field is also included in this first smart camera that, let's say, came to birth in 1996. These principles still lead the way for us, and it really shows what embedded vision means to us here at Vision Components. Our goal is always to choose the perfect components to create the, let's say, best possible products and components for our customers. Over the years, we of course evolved together with the technology. When we started in 1996, when Michael Engel developed the first smart camera, we started with DSP technology from Analog Devices. From a performance point of view, let's put this on this level. Then we switched to TI DSP technology a couple of years later. Then again, after a couple of years, switching to ARM, a combination of ARM-based technology with an FPGA based on a Linux operating system. Nowadays, of course, we are at multi-core ARM platforms in combination with GPUs, FPGA. So it's really a multi-platform architecture that can be used. Then when we go to the world of the MIPI, the most flexible way, of course, you have the complete doors open to all the CPUs that you can find out there. So really starting with SOMs like the Raspberry Pi over NVIDIA modules, NXP with the latest IMX8 processing unit technology. So you have the complete broad range open for you to be used in your embedded vision application. And that's really our goal over the past 25 years, and this will go on the next years, of course, is always to give you the opportunity to use the latest technology in both, of course, image sensors and processing unit to create a successful embedded vision application. So now, starting with the technology, as we've heard at the start, level 1 would be using MIPI camera module. With the MIPI camera modules, you have the highest flexibility because you have a broad range of sensors that you can use. And then we can start with the sensors having a native onboard MIPI interface. So just now starting with the IMX 296, 1.5, 1.6 megapixel sensor, Sony Pregis series, monochrome, color sensor, very compact design. We have a small board of 22, about 23 millimeters of physical size. Of course, as we are used to, it's a perfect industrial design for heat dissipation, perfect fitting and mounting into application. And then I was talking about a broad range of sensors. So this is just one of those. You can then go with the OV9281 from OmniVision, global shutter, monochrome, 1 megapixel, through from Sony IMX 273, IMX 183. Then, of course, we are talking about a different class of sensors, which do not come with a native MIPI interface on board, but that's not an issue for you because that's something that we did on our side. We created the MIPI interface for these sensors, so it's not an issue for you. It's just standard MIPI output that we generate over the second interface board that we just add to the sensor board itself. That means if you go with these MIPI sensors, what you need, of course, then is a perfect cable connection between the MIPI sensor and your CPU device. But then you have the choice on the CPU side. Do you want to do some rapid prototyping? You can use a Raspberry Pi. If you want to use a high-end SOM or high-end module, including AI capabilities, you can choose one of the NVIDIA platforms, or you can choose one of the NXP IMX8 platforms. For all these platforms, of course, we do not only offer the range of the MIPI modules, but also the drivers. Because one thing you do not have to forget, without the driver, you will not be able to communicate between the image sensor, the MIPI module, and the CPU that you have on the other side. That's a very important point that a lot of people forget about, but that's something, of course, we offer for free in addition to all the MIPI modules, including the source code. So you can use the basic functions that we deliver within the driver. But if you like, you can also modify it because you get the source code in your hands as well. Of course, to create an embedded vision system, the MIPI module is one thing, and then you need accessories to create the full system. So first step, of course, is going from the camera module to your CPU board. You need a cable. It sounds easy, but it's very important to make the right choice, not to have any interferences between the image sensor that creates the image data and the receiving part. So it's very important to choose the right cable. Of course, we're also offering high-end cables to allow a very robust data transmission to a 22-pin or 15-pin solution on the CPU unit. Then you need the CPU unit. That's something that is in your hands because maybe you have already made your choice to use a board from NVIDIA, a Raspberry Pi, a board from NXP, or any SOM manufacturer that integrates a certain CPU on the board. In addition, we can also help with additional service in creating a carrier board. If you've chosen a specific SOM, but there's no fitting carrier board for your application, you can do it on your own. That's no issue, or we can guide you to an appropriate partner, or we can help in the design, because this is something you're going to need to be able to have all the interfaces that you need to the outside world, meaning IOs, communication interfaces, or then video output. With these three elements, camera module, cable, CPU board, and carrier board, you have a functioning embedded vision system for which we can, of course, offer additional accessories such as a lighting module, lens holders for the different lenses. So all of this you can get from one hand, or we can guide you through OEM sources to really source these specific components at the best OEM conditions possible. Now we come to level 2. many OEM applications have a high demand for the highest integration possible. And that's where our board level cameras come into game. They combine everything on a very small footprint of 40 by 65 millimeters. They integrate the image sensor, the CPU, the interfaces, the memory, everything on one board. That means you have a full system loaded with the standard Debian Linux package. It comes with digital IOs, trigger input, flash trigger output, I2C bus, serial link, battery buffered real-time clock, gigabit Ethernet interface. And of course, you can have different versions regarding the computational power of the system that you need. It could be a dual-core ARM combined with an FPGA, or it can also be a quad-core ARM with 1.2 gigahertz. Both of them running a standard Linux on board already. So you have no issue with drivers or to adapt your drivers with an external CPU. You have really highly compact and highly optimized standalone system, ready to play with, ready to get your program running. Depending on your application, of course, we're having different camera modules with different types of sensors. So you can choose, again, the right sensor for your application. We've seen earlier we started with a version with a sensor on board. We, of course, also have the remote head sensor option. That means you can have a sensor board with one remote head to have, again, very high flexibility of setup options within your project, within your own housing. And you also have the option of adding a second sensor, meaning you can attach two sensors directly connected to the same board with internal synchronization of the two heads. Everything is done within the hardware. So this is also a very nice and highly optimized way of creating, for example, a stereo system. You have the two sensors attached to one board, and all the synchronization is done internally within the board by hardware. Now we're going to the third level of integration, meaning a ready-to-use embedded vision solution. And for this, I will just go and show a typical application, a typical product. But wait, I think we will bring this on the screen to get a better picture. If you look at this, you will see exactly what we've been talking about earlier. You need the image sensor, meaning a camera module. You have the CPU unit. You have an interface board. In this case, we are also having a light source, which is a laser module to generate the laser line to get profile data then onto the system. In this specific case, we're using an SoC, which is using a dual-core ARM and an FPGA in one chip. The FPGA is doing the complete calculation of the laser line. So this is generating the point cloud for the 3D measurement. Then all of these contour points go into the internal memory where we have the dual-core ARM and the Linux operating system, which is fully ready to then calculate whatever you need for different application within the processor. So you can easily do volumetric angle measurement. You can do a gap measurement. You can do a minimum maximum measurement, absence presence control. So any type of application that you can think of that can be done with laser triangulation would be a perfect fit for such kind of a very compact embedded vision solution. And then, of course, for a lot of different applications, the final solution will look different, but there's almost no limit to embedded vision or for the use of embedded vision components we could think of right now. So now we come more or less to an end. If you have any plan need or to develop or to implement an embedded vision solution, always think of the different steps that you may take, starting from the MIPI camera modules, the fully embedded board level cameras, and a ready-to-use system. So we at Vision Components, we're doing this for about 25 years, and we would be happy to support you into your next embedded vision solution project. So now it's your turn to make the right choice for embedded imaging, and that means choose Vision Components. Thank you.